Are there any questions before we continue? Angular momentum or the moment of momentum balance. Now the momentum of a body of fluid is given by this. This may be regarded, as I said, as a momentum density, the momentum per unit volume. You have to integrate that over the whole region. Can you open the door? So the moment of momentum is the moment of the momentum density. We regard this as the moment of the momentum density, or the angular momentum density, right? And then you can have to integrate that over the volume, and you get the angular momentum or the moment of momentum associated with that body. Now the time rate of change of that, this is the principle of angular momentum or the angular momentum balance, is given simply by the torque, as it is called, exerted by the forces. These are the moments of the forces. So you have the body force moment and the contact force moment that's given by those two terms. So this is the basic moment of momentum balance. Right? So we introduced now a new operation, that is a vector or the cross product of two vectors. So we discussed that briefly. So to define that, this is the net result is a vector. That is what's called as a vector product. We've already introduced a scalar product of two vectors as well as the tensor product of two vectors. So in the first case, the net effect is a scalar. The second case, the net effect is a tensor. We've already considered those two. Now this one is a vector. So you can write the I component as epsilon I j k, quantity which we have already introduced, a j b k. So the vector itself can be written in this manner, and in comparing with the formula for the determinant of a 3×3 matrix, I can simply infer that this is the determinant of the matrix, one of whose rows is given by the unit vectors E1, E2 and E3. The other two rows are given by the components of the two vectors, right? That is another way of writing this. This is the cross product of two vectors. So when you're looking at, let us for instance take the I component. You often, while doing manipulations involving the cross product and another operation that we introduce called the curl of a vector, are the two more difficult of the various operations. Right? That's why you will find the vector identities that you have asked to prove. Many of them involve these operations, namely the cross product of two vectors. And another one we haven't encountered yet. It is called as the curl of a vector. That also, the net result is a vector. Right? This is also a cross product, but this involves the derivative operator, gradient operator. It can be written similar to this. You will see shortly how to write. Now, if you look at this, Eijk, AJBK. Now, I'll write two other terms with a slight modifications of this. Suppose I make this EJIK and then I write EIJK, AKBJ. We might have to do these kinds of manipulations in proving some of the identities, so that's why I'm introducing that. Now, admittedly, you might ask, why do I need to write this? You might have to do it. That's why I'm now informing you on how to do this. Now, if you consider this, these two, you can easily verify that this is equal to the negative of this, right? And this is simply equal to that, the second sum that I have written. First of all, it is very clear, in both cases, both are sums over j and k, right? Both are sums over j and k. You will find that this would be the negative of this, right? On the other hand, this is equal to this. So, one way of looking at it, you will compare these. The only change I have made is I have interchanged j and I. No other change has been made. Right? So in which case, right, it's an odd number of interchange, so you have to make it negative. Now, the best way to verify this is simply apply this. Let us say I take I equal to 1. I fix I equal to 1. Right? So it would be E1 JK. This is the first term I am looking at. E1 JK AJ BK. This is a sum over J and K. J runs from 1 to 3 and K runs from 1 to 3. However, because of the property of the epsilon I j k, I only have to consider the possibility of j and k being 2 or 3, right? So the first possibility is this is epsilon 1, 2, 3, a2, b3 plus 3, 2, a3, b2. Only two possibilities for j, because already 1 is fixed. J can be either 2 or 3. The moment I have chosen j to be 2, k, which can not be 1, it cannot be 3 anymore. So the only terms that will come out are these two terms, even though it's a sum over j and k running from 1 to 3. This is what I have. So this is clearly a2 b3 minus a3 b2. Now I look at the next one, ejik is equal to, right? Now the I is still not a summation index. J and K is still summed over J, but I have shifted the indices. So let's see what this is. So again I equal to 1, right? So again J can be either 2 or 3. But J is 2, this will be 2, 1, 3, A2, B3 plus J can be 3, 1, 2, A3, this would be 2, 1, 3 is epsilon 2, 1, 3 is minus 1. So this would be minus A2, B3 plus 3, 1, 2 is 1, epsilon 3, 1 plus. So clearly this is the negative of this. So this is correct. So whenever you are doing these operations, you are just interchanging two of the indices. I, and here I is not a summation index, but J is. Here what I have done was slightly different. I have interchanged J and K, but I have interchanged it throughout the expression. So when we do that, right, what all I have done, this is sum over J, this is effectively sum over K equal to this one, if I want to write it. J equal to 1 to 3, sum over K equal to 1 to 3, epsilon 1. JK. I'm just taking I equal to 1. Right? So this is an unrestricted sum over both J and K. There is nothing that prevents me from writing this as all I have done is interchange the indices, summation indices. Choice for the first summation index J is totally arbitrary. I will use it to be K, right? So all I have done is interchange the indices entirely throughout the sum. All that means is that instead of summing it, writing the J equal to 1 to 3, and k equal to 1 to 3. I've written it as k equal to 1 to 3 and j equal to 1 to 3. That's all I have done. Right? So no wonder if I were to now write that, the best way is to check this. So that would be E1 kj A k bj. Right? So that would then be E1. Right? So now I can look at again j equal to 2 and then j would be 3. E1 3 2. Right? j equal to 2. Right? So that would be A3 B2 plus j equal to 3, k would be equal to 2. 1 2 3. J equal to 3. Right? K equal to 2 that would be A2 B3. Which is this is minus A3 B2 plus A2 B3. It's exactly the same as what we have. So when you have to see what I am doing in this case here. I'm just interchanging the indices in the epsilon alone. We've already seen that is an odd number of interchange. Effectively, that means, right? Still j runs from 1 to 3, j runs from 1 to 3, but because I've interchanged the position of j once, right? So I'm going to get negative. Wherever I got positive, I'll get a negative. When I'm getting negative, I'll get positive. So that's what I'm doing. Here two summation indices are there. I'm just interchanging them throughout the expression. That will not affect the sum at all. Right? So if you want, I can always write this as some L and M, but I'm perfectly allowed to do it. Right? I can replace it by L and M. Then I can replace L by K and M by J. If you're confused about my interchanging of the indices, you can do it in 2 steps. Call it some other L and some other M instead of J and K. And then I'll forget that I had J and K earlier. I'll call L as K and M as J. Right? So that should not be a problem. So you have to understand how to manipulate these indices, because what might happen is sometimes because this is giving me the ith component, right? So this is giving some place you might need the kth component of A cross B or the jth component in the way you have used the index. So you don't always want to be constrained, with just this formula. You should be able to get what the jth component or kth component would be by suitable modification, right? So we'll encounter that when we actually do the problem. Right now I'm focusing on the cross product of two vectors as they appear, because they appear in the moment of momentum balance. Right? So now our main purpose is, this is the overall momentum balance applied to the body as a whole. The first step is to get a local momentum balance. And so I'll quickly go through that. Now, you've been asked to prove actually the stress tensor is symmetric. So I'll just quickly go through the steps. So you can see here, the first step would be to write this as d by dt, because you can easily verify that if I have a constant, let's say, it's a scalar, it's not a constant, it could depend on the coordinates x, y, and z, or x1, x2, and x3. So clearly, I can write this as 4 times the scalar can be taken out. Right? You can easily verify that. Right? So if you have phi A cross B, you will get the ith component. So this would be phi AJ. Right? That can be, the phi can be taken out because it's not part of the sum. Right? It can be written as phi times. So clearly phi A cross B is equal to phi times A cross B. Right? So I can write it this way. The rho can be taken out. If you recall, one of the formulas or versions of the Reynolds transport theorem was that d by dt of rho times something, right, is simply given by rho d by dt of that something. We used it in the case of a scalar, but can be easily generalized to that of a vector. I think I asked you to prove it. We had to use the continuity equation. I don't know how many of you attempted to prove it, but it can be easily proved this is the next step. Right? I'm just proving one of the assignment problems. I won't do the whole thing. So now you have d by dt of a cross b. So both are functions of time, and you can easily verify simply using this formula. Right? Simply using this formula, because here when I talk about general vector, I am not saying what they are dependent on. Here I am dealing in fluid mechanics with something that's a function of either the spatial coordinates of time or the material coordinates in time. So obviously when I am talking about d by dt, I am talking about both x and b being expressed in terms of the material coordinates. Right? So it's easy to show that d by dt of a cross product is given by a cross dv by dt plus dA by dt cross b. So I continue to differentiate A and B separately. The order is very important. The same way it's possible also to show the dot product. This is now a scalar, right? This can be easily shown to be A dot. Here the order doesn't matter because it's a scalar dot product. Here the order is very important. To preserve the order, A always comes first, whether you differentiate it or not. Plus, what I'm trying to point out, I can easily write this B dotted with dA by dt, but here I cannot do a B because that will be negative of that, right? Because the cross product has a sign associated with it. This is a vector product. So I get this. So now this would be rho. So I can write the same thing, bx by dt cross b plus x cross now you show that this is equal to rho x cross dv by dt, which means that this is 0. Now, why is that 0? dx by dt cross b, why is that 0? Both of them are velocity. So dx by dt is nothing but b. And you can easily verify from this if I have simply a cross a. Two rows of a determinant of the matrix are the same, so the determinant would be 0. That can be easily verified. Now, in developing these expressions, I have sort of taken a shortcut in that I have not defined what are the operations, corresponding operations on the unit vector. Strictly, I should define that first, and then these products such as these become easily obtainable. For instance, when I take the dot product of two vectors, I directly introduce the formula in rectilinear Cartesian coordinates. You will find that when you go to curvilinear coordinates, for instance, it will not be that easy to write the dot product always. Right? So, what is implicit of all of you know that actually, let me just briefly take a diversion. So, what I mean here is that E1 dotted with E1 is clearly 1. Right? And E1 dotted with E2 is equal to 0 and so on. So I can compactly write this as EI dotted with EJ is equal to delta IJ. Right? So strictly I should have defined any operation by first defining what would be the action of the unit vectors, and then the formula for a general product or sum or whatever becomes very easy to derive. But I sort of avoided this step. Right? For instance, if I now making use of this, if I were to calculate A dot B, I would write this as AI EI. Repeated index is used here. Dotted. Obviously, I don't want to use I for B also, so I will write this as BJ EJ. that would then become AI Bj, right? EI dotted with Ej is AI Bj delta Ij, which is simply AI Bi. So rather than doing this, I simply directly gave you what the dot product of two vectors would be in Cartesian coordinates. In the same way, I have given this for A with the cross product, but you all know that here E1 cross E1 is 0, E1 cross E2 equal to E3 and so on. The cross product of any of the unit vectors with respect to itself is 0 actually. The cross product that is 1, 2 will give me E3. So obviously 2, 1, E2 cross E1 will be minus E3. In the same way I can define the other cross products involving two vectors which are not the same. Right? So maybe E2 cross E3 would be equal to E1 with that order 2, 3, 1 if you see. So E3 cross E2 would be equal to minus E1 and so on. All of this you know. But you can easily get all of that by the general expression I have given. So here you can clearly see that you have the cross product of a vector with itself. So that is 0. So now I have got this. So now I will simply take the row inside, right? And then I have x cross rho b. So both of them are volume integrals. So I can write this as finally simplified form as integral x cross, again I have x cross rho dv by dt and I have x cross rho b here. I'll bring it over to this side, then I'll bring the x cross rho b and this into the same integral. That can be done. And then I will again use the formula that a cross b plus a cross c is simply a cross b plus c. Those are very intuitively clear and you can easily verify them using this formula. Right? So I will write this as rho dv by dt minus rho b. That much I have. So all clearly, if I want to get a local angular momentum or local momentum values, I would have to convert the integral over A into 1 over B. For that I need to use some form of the divergence theorem. So that is where you would need to work on that's what we will do now, right? So I take again the ith component of this and find out what this is. So I am looking at x cross t I. Right, so what can you tell me what that will be using that formula epsilon I j k? Xj Tk. That is the ith component, all I am writing. I want to focus on the ith component. So this is what I am going to follow. If you are comfortable writing the whole vector out, then you would have to add an ei. For me, that's an additional problem. As it is, I have to deal with sum over j and k. Why do I want to impose an additional sum over I when I can simply focus on the ith component and then put everything together at the end? That's the idea I will adopt throughout. In the same way, if I have to work on a tensor, I will simply take the ijth component and work with it and finally add everything together and conclude what the tensor identity is going to be. Right? So now here, clearly I need to bring in the stress tensor. So you can already see the two parts of the equation of motion have come into play. So So good guess that the third part, which involves the divergence of a tensor, the stress tensor, is also going to come in. So now if I want to write, we know that T is equal to n dotted with T. So how would you write the kth component of the stress vector T? Can you look at the formula sheet that you have? What we want is A dot I, but what you will have is the ith component given. So from that, can you tell me what the yeah, fine. You tell me the formula Tk. So what I want is Tk. So this is the first test on how comfortable you are in making use of the formula that is given in a given case, like this, right? I'm not asking you for the ith component, I'm asking for the kth component of T. What is Tk equal to? Nj Tj K. Now this is fine independently, but can I apply this here? Exactly, because J is already used as a summation index. So there's already a sum over J going. So if I want another summation index, right? If I put Tj, Nj, Tj, K, there's already a sum J equal to 1 to 3, K equal to 1 to 3. Now I want to look at this. So I don't want to use J equal to 1 to 3, or for that matter K equal to 1 to 3. I'm sorry. Yeah, exactly. So K equal to 1, K cannot also be used, and here of course you cannot use K as a summation index. That's very obvious, because I want the kth component. So that confusion will not arise. But you have to understand that since J is already in the sum used as a summation index, I have to use some other index. So I can use L. So I can write this as NLPLK. Right? So that's what you have to understand. Now this is a sum over J, K as well as L. I is the only particular component I am looking at. So I cannot be a summation index anywhere. Right? So the formula introduces two summation index J and K. Now I got a formula for Tk. So it's already a sum over I, J and K. Okay, so I have to find another. So it's actually sum over J, K and L. You can easily figure out if you were to continue to use J as the summation index here, you would definitely go wrong, right? That you can easily verify, because that would continue to be a sum over just J and K. Now I have a sum over J, K and L. This is one of the disadvantages of the repeated index summation convention. So you might not immediately recognize which is being summed over. You can always keep that in mind. Because repeated index is being summed over, right? So there's both advantage and disadvantage. It is a convenience. Once you get familiar with it, then it's very convenient to use. So now, obviously, I am looking at the ith component integrated over A. Now this is certainly in a form, I'll write it like this, where I can use the divergence theorem. Because to use the divergence theorem, which is given also in your, I have Fni dA is equal to F comma I dB. Right? That's how it is given. I'm just saying. Now you tell me how you would, what would come in the integral over B. What is F here? This is F. Very easy to figure out. Right? This is the F. So whatever doesn't have the N, whatever is left behind is the F. Right? So F is simply Eijk xj PLK. Now what would come here? Comma L. That's very important. There are three summation indices. You should know which one will come here. So the derivative with respect to xl, and then summed over L, and of course J and K have also been summed over. Right? So what determines what comes here is obviously what comes here. Here it is NL. So clearly I have to take the derivative with respect to XL. Summation over L is already implied. Right? So you can see the power of this generalized divergence theorem. It helps you to apply it in some totally arbitrary case. We don't even know what this quantity actually represents. Right? So now I have this. Now I clearly have got a stress tensor in. So now clearly how would you proceed now? How many terms are there that have to be differentiated here? 3. This is constant. I don't have to differentiate this. Obviously, these two, they're all in the derivative. I can clearly split that. So let's split that. Right? And keep the product rule of differentiation I am applying. Again, you have to know what the comma L represents, the derivative with respect to xl. Right? So first I differentiate xj with respect to xl. That becomes xj comma L. tlk, I don't differentiate that now. The next term, I'll leave xj as it is and differentiate dlk. So what is xj comma L? dxj by dxl. What is that equal to?
0.
It's actually equal, not quite to 0. Delta JL. Right? So this is very important because we earlier differentiated x with respect to psi, and there was always a confusion. How can you differentiate, x is the spatial coordinate? How are you able to differentiate it with respect to psi? Right? The problem is there. The x was a dependent variable, so I was actually differentiating that xj expressed as. Here that is not the case. Here x1, the partial derivative with respect to xl means I am looking at the representation in terms of x1, x2 and x3. So when I am differentiating xj with respect to xl, right, that means what? That is like saying dx1 by dx2, for instance. That will clearly be 0 because this is expressed as a function of x1, x2 and x3. So I am differentiating with respect to x2, keeping x1 and x3 fixed. So x1 cannot be differentiated, derivative will simply give 0. On the other hand, if I do this, then that's clearly equal to 1, right? So if j is different from L, you get a 0. J is equal to L, you get a 1, right? So clearly the value would be delta j, and that's very important to keep in mind because there's a sum over j and L running. So you cannot just treat it as 0 or 1 for that matter. ELK plus so further this can be, now this is the sum over j, L and k, but the sum over j and L can be combined to simplify the expression, right? So if you look at the sum over j and L, only those terms for which L is equal to j will contribute. That would be 1, all the other terms would be 0 whenever L is not equal to j. So I can choose either L or j to retain. I choose j, then that would be epsilon ij k djk, or I can make it epsilon I L k dlk, right? But I am choosing to retain j. Now what about this? What can you say about TIK dotted with, comma L? That's clearly the divergence. If you look at the divergence of the stress tensor, the height component is Tji, comma J. So I am looking here at the height component. I have used J as a summation index. That's how the formula is given in your formula sheet. So maybe the tensor A. Now what can you say about TIK?
Kth component. Kth component. L dot TK.
Yeah, so that is the kth component of the divergence. So this term, the second term, right, the first term is epsilon ijk tjk. The second term is epsilon ijk xj, the kth component of the divergence of the stress tensor. L is here coming as a summation index, but K is the one that is not summed over this term alone I am looking at. That I will write. So clearly, this is nothing but, what can you say about this? The formula is right there. Epsilon ijk, aj, bk is a cross product of vectors A and B, right? So clearly, now this would be equal to this is the ith component of the cross product of x with the divergence of the stress tensor, right? So here it's again a cross product of two vectors, but one of the vectors is the divergence of a tensor, right? So I can write this as the ith component of right? That's what I have. Now I'll go back and write the vector equation, because here I have a vector equation. I want to focus on this. I took the ith component. Now I want to put it back in vector form, right? So clearly then, if I'm going to write the right hand side alone, it's now coming as an integral, because this is all of this I took it separately, right? So this is now an integral over the volume, right? So first term is epsilon ijk, tjk. That is some quantity. I have to look at it what it is now. So it's the ith component that I am getting here. So clearly, if we want to write a full vector, that would be, right? That would be ei. I have to add that because that's the ith component. I am getting a scalar. That's the ith component of the full vector. The full vector is obtained by simply taking each of the components and then multiplying by the corresponding unit vector. So that's what I get. This, of course, would simply be the ith component of x cross divergence of stress tensor. So I'll simply write this as x cross the vector itself. Now we are close to proving the symmetry of the stress tensor. Now what I do here is that now I will bring this term alone to the other side. So what I have here is x cross minus rho v minus is equal to over v volume what can you say about the left hand side? Zero, because the equation of motion, we've recovered the equation of motion, within the integral. So here there is no problem. Equation motion we have proved to be 0 at every point within the fluid. So if I integrate 0 over the entire region, I am going to get 0. Right? So I get 0. So what I have obtained here is that equal to 0. Right? Now this is effectively equivalent to proving the stress tensor is symmetric. So to do that, there are 3 equations here. Each one of the components are 0. Right? So if I do the first component, I get E1 jk equal to 0. E2 jk E3 0. If I apply this, here I is taken to be 1. So this is clearly E1, 2, 3, E2, 3 plus E1, 3, 2, E3, 2 equal to 0. So now this is 1, this is minus 1. So this will imply that E2, 3 equal to E3, 2. Now this one is 2, 1, 3, D1, 3 plus E2, 3, 1. P3, 1 equal to 0. Again, one of the epsilons will have positive 1, another will be negative. So from that, you will clearly show P1, 3 equal to P3, 1. And from this, you can show that P1 equal to 2 equal to P1, which implies that P is symmetric. Because that is the definition of a symmetric tensor, is that the off-diagonal elements are equal. Of course, there is no restriction on D1, 1, D2, 2 and D3, 3. They can be arbitrary. Clearly, the off-diagonal elements must be equal to each other, which means that the stress tensor is symmetric. This is very important because often for mass point mechanics, the momentum balance is not regarded as a new principle. You have the force balance, you just take the moments of the forces and you are simply doing the same thing. I mean, if you have A equal to B and you take x cross A, it's obviously going to be equal to x cross B. However, here we get something new, right? Because we have a force balance to begin with. This is the local force balance, right? X cross Z will be 0. There's nothing new that we get out of this. But by applying the momentum balance on the body, what we have been able to prove as a result is that the stress tensor is symmetric. So the symmetricity of the stress tensor is a consequence of the momentum principle. Now if you look at Aris, he points out that for certain fluids, which he probably calls polar fluids, but those are not the polar in the same sense which we are all familiar with, there will be additional terms which are not necessarily coming from the moment of the forces on the right hand side. Some additional stresses have to be added, right? Some additional terms which are involving the moments of the certain other stresses have to be added, in which case we will not get the stress tensor to be symmetric. So the fact that the stress tensor is symmetric is not a general law, because there are cases apparently, I am not very familiar with such cases, where this is not all of the angular momentum balance, but there will be some additional terms, in which case that additional term will come in and you will not be able to prove that the stress tensor is symmetric. But however, in this course, we will restrict ourselves only to those cases where the stress tensor is symmetric. That is, we assume that the momentum balance has this form. We will not get any more general than this. For our purposes, always stress tensor will be regarded as symmetric. Are there any questions? Because we've come to the end of the class and tomorrow we start probably with the assignment. One new operation I haven't introduced is the curl of the vector. I haven't defined it. Formula is there, right? So we start solving or proving some of the identities that are there in the first part, and also I'll tell you what you need to do to complete the rest of the proof in the second part of the assignment, right? That I'm not going to do that. That I will let you do. Now what is left is, we've got proof that the stress tensor is symmetric. Now we want a control volume balance for the moment of momentum. That I will let you to prove it, but I'll just give you an outline of that proof in tomorrow's class and let you fill in all the details. After that, we will look at the vector identities and scalar identities that are given. The first part of the assignment, we try to prove them and see what are all the complications that could arise, confusions that could arise. If there are no questions, then that's all I have to say for today.